Hello everybody and welcome to meeting Part L 2019 with KORE Insulation and Uni-Therm heating systems. This morning we're going to be looking at the benefits of building with KORE Insulation and Uni-Therm heating systems to meet Part L and Part F 2019. Our first speaker this morning is Andrew Butler, Technical Manager at KORE Insulation, who will be discussing the importance of a fabric-first approach, creating a thermal bridge-free design at the wall-to-floor junction with KORE's insulated foundation system and floor insulation, looking at the benefits of both, real-life case studies, costings, and more. Following Andrew, we have Liam Jordan, Technical Sales Engineer from Uni-Therm, who will be discussing Uni-Therm heating systems, including the LG Therma V or 32 heat pump to meet NZEB underfloor heating systems, the integration with KORE's insulated foundation system, certification, and more. So without further ado, I will hand you over to our first speaker, Andrew Butler from KORE.
Thanks, Lisa. Welcome along, everybody, today. Thanks for joining us. As Lisa mentioned, we're doing a joint CPD today, so hopefully everybody will get something out of it. I'll get my screen on now in a second. We get started. Okay, there we go. So that's my email address, andrewbutler@koresystem.com. I'll have it on the last slide as well, just when I finish up. Just if anybody wants to send me anything directly, please do. There's also the Q&A function there if you want to pop any questions in as we're going along. For either myself or Liam, sure, pop them in there and we can answer them at the end. So we're going to talk a little bit about floor insulation and our insulated foundation system today. So a little bit about ourselves first. KORE Insulation. So we manufacture EPS or expanded polystyrene. So when I talk about EPS during the presentation, that's what it means, expanded polystyrene. We're an Irish company, guaranteed Irish, family-owned company in operation over 24 years, based in County Cavan, but we cover the whole country. We also supply materials to the UK. We've NSAI certification for various products. We have all the ISO up-to-date certifications. We were actually the first company in the country to get all the up-to-date ISO certs. So a little bit about EPS first, expanded polystyrene. So we have this picture on the left-hand side here. These are the various forms that we'll see EPS in. So this very small kind of granular material here, what we call the sugar, it's the raw material. All that we need to do really to make our EPS, I'll try and make it sound simple, of course, it's probably not that simple in practicality. We hit it with steam and we hit it with some heat and we expand the raw material into the bead form. The bead form can be used for various things, including cavity wall insulation. After that, we can take the bead and make blocks. So we put it into like a big oven, essentially, a block mold, and we make these large blocks. And as you can see in the EPS, there's a white EPS and what we call a silver EPS. And in those, there's different densities, different strengths, but they can be made into pretty much any shape and thickness that the customer wants, depending on the project, depending on the use. That's the great thing about EPS. It's very flexible from that point of view. So that's a little bit about EPS. And why would you use EPS? Because God knows there's a lot of insulation materials on the market at the moment, and it's, I suppose, can be a little bit bamboozling trying to figure out which one should you be using, you know, what does what. So EPS works very well as an insulation material. It's 98% air. EPS doesn't decompose, so it doesn't change over the lifetime of the building. So day one, when you specify or use an EPS material, the thermal performance and the physical performance does not change. And that's very, very important. Compared to other materials, they may off gas, lose their thermal conductivity over time, lose the performance. EPS does not change. And a very welcome thing, depending on the product and what you're using it for, EPS can offer a price performance ratio, which is really good compared to other materials that are out there. Not today, thankfully, because it's lovely and bright and sunny, but if you're using EPS on a site that's wet and damp, there's no issues using EPS. You can actually pour concrete straight onto it as well, and it doesn't get affected by it. So that's always a very welcome thing. Light, practical, easy to work with on site, even just cutting it. There's no dust that comes off of it. In terms of its environmental credentials, we would consider it an eco-friendly material as a man-made insulation material. As I said, it's 98% air. It is recyclable. So even at the end of life of building, the material can be recycled. We recycle all our offcuts in-house so we don't waste any. There's no gases used in the performance of the EPS. So as I said, all we hit it was with steam and with heat. We don't inject any gases into it, and it doesn't off gas over time. And as you see, when I get onto our insulated foundation system, how we can shape it and cut it and do lots of things with it. So just a very quick thing, I suppose, on building regulations, and Liam's going to talk a little bit more about it from the point of view of the heating systems as well. So the big thing that we're looking at today is the change to Part L, which came in 2019, and there was a transition period up till the 1st of November 2020. So from then on, the new Part L is fully in place. But what we're concerned about today is the floor from the EPS that we're looking at today. So 0.18 is our new backstop U value. So that's the minimum we need to achieve in a U value in the floor. If we're using underfloor heating, this needs to be 0.15. So I think a realistic view of the industry at times, and depending where you are in the chain, whether you are a specifier, a builder, a home builder, wherever you may be, there's a lot of pressures, issues, and especially now, I suppose, with the way things have been with lockdowns and that kind of thing, we're trying to find ways to make life easy for ourselves. Why overcomplicate things? As we mentioned at the intro, if we look at the fabric, get that right, get a good heating system into the bills, it's going to solve a lot of problems for us. By using something like an EPS, we're hoping we can resolve some of these issues. So there's a lot of issues, again, around compliance with the building regulations, trying to get to our U values, trying to get the technical backup that you need for a product, issues with maybe skilled labor, lack of skilled labor, time constraints, there's a lot of pressures out there. So by using something like an EPS, hopefully we can resolve those problems. So first, we're going to just have a quick look at our floor insulation. So this product here is what we call an EPS 70 silver board. And that's probably 90% of our floor insulation, certainly for domestic and light commercial market. So it's the silver color. The silver compared to the white EPS has a lower thermal conductivity, which means you need less of it to get to the required U values. That's essentially the difference between the white and the silver. So we're going to look at a few targets and some U values as well as we get into this. So just to make you aware of, I suppose, that I mentioned at the start, we've different densities in EPS. So we've an EPS 70 silver and white, and we go all the way up to an EPS 300. So that's a 300 kilonewton per square meter strength material, or KPA. So we're using that, and you see that in our foundation system where we're using heavy loads and we need to take structural loading. But as I mentioned, most of the time we're using an EPS 70 silver board for a domestic situation, whether it be under a floor slab, or as we see here in this cutaway, we have it under a screed. And there we have our underfloor heating pipes. Hopefully you go with something like a Uni-Therm system here, which will work really well with the EPS. And as I mentioned, because it is EPS, you can pour the screed straight onto the EPS. You can pour the concrete straight onto the EPS. You don't need a separation there. For easy compliance, and again, depending on where you are, whether you're a specifier, a designer, an architect, even just a user of the material, we have our NSI agreement cert, all up to date, revised recently. We have design guides. So if you're looking to use an EPS product, we have a design guide showing all the build-up details that you can use the material in. And we also have thermal modeling. So we've the psi values and all that kind of good stuff worked out. So you can use our details, you can use our thermal modeling, which means compliant with your A ratings and your deep calculations for your BER requirements can be gotten a lot easier. So if you just use a standard detail in the industry, so an accredited detail, you get a psi value of 0.08. If you're using one of our enhanced details, you can use the thermal modeling that goes with that. Now, there's only a couple of handful of thermal modelers registered with the NSEI, which one of them we use to create our thermal model. So you can get to your energy ratings easier. All our products have CE marks and DOPs as well. So in terms of the floor insulation, just in a standard traditional type build, we can supply the EPS in any thickness that you want, from 10 millimeters up to whatever you need. So that's the beauty about EPS. It can be bespoke. So you could say if you had 150 millimeters of floor insulation, you can do it in 2 layers, whether it be a 75 to 75, 150 mil, you name it, we can make it. That's it. So a couple of floor calculations for you first. Typical scenarios. For both of these, we picked a perimeter area ratio 0.4. So your perimeter versus your area of your floors. So standard build, we have a 75 mil screed, we have an insulation, and we have a 150 mil subfloor. So if we're using underfloor heating here, our U-value target is 0.15 to comply with our building regulations. To get there, all we need is 150 mil of our silver EPS. Now, bear in mind, if you're using an EPS, it should come in cheaper than a different product that's out there. You should have good conscience in the fact that your product is going to perform. So what day one versus 50 years versus 100 years down the line, that floor insulation is doing exactly the same thing from its thermal and its physical performance. That's not going to change. So that's always really good to know. Looking at a different type of buildup, so where we might have a concrete slab straight onto insulation. And again, we have the same perimeter area ratio, 0.4. We'll need 160 mil for that buildup of our EPS 70 silver. Again, to hit that target of 0.1 floor or 0.15, where we're using something like the underfloor heating. And again, because it's an EPS, works very well with the underfloor heating system. So they're just a couple of examples. As I mentioned, we have a design guide showing tables, all sorts of thicknesses, U-value targets. So you could use 200 mil in there, get a lower U-value, obviously. And because it's an EPS, you can get to the lower values quite easily and quite effectively in terms of the cost. Just a little bit on the commercial end of things. So as I mentioned, we do up to an EPS 300, which is that really strong material. So we would usually see that being used in the likes of the car showroom. So you see the new Joe Duffy development in Dublin at the top there. Bottom left corner here, we have the Combi Lift factory in Monaghan, where they have very heavy loads running around, obviously moving on that concrete slab. So they're using a much denser material. That was a project there in Ballsbridge in Dublin. I think it was one of the most expensive sites at the time, but they used an EPS 70 white between the screeds and their floors in the office and the residential development there. Just to make you aware of it. Okay, so a little bit different now. So we're going to look at building slightly differently. So up until, I suppose, about 10 years ago, the main model you'd see for building ground floor was strip foundations or a raft foundation. So a insulated foundation system kind of looks a little bit like a raft foundation, but it's kind of flipped around a little bit. So the model for this building came from the Scandinavian countries. They've been building this way for the last 30 to 40 years, very effectively. And the whole idea is we're trying to make life easy for ourselves. We're trying to build cost effectively. We're trying to build with a little bit of speed, and we're trying to reduce our thermal bridging. And do it effectively with a material, again, that because it's an EPS, we know it's going to perform, it's going to last, it's not going to change over time. So when we look at traditional build strip foundations, we're coming onto a site, we come along, we strip our vegetation, our topsoil. All right, we're going to do that as well with this type of build. So nothing different there. Where the similarities stop is just at that point. If we're looking at strip foundations, we're digging trenches, we're pulling up muck, we're putting down concrete strips, we're bringing up rising walls. If we're using an insulated foundation system, we don't have to do any of that. So we're taking out a lot of the hassle factor. As I said, we're trying to make life easy for ourselves. So why would you use an insulated foundation system? Well, it's more than NZ and Part L compliant. We're going to reduce the cost, certainly when we get into multiple builds. We can possibly save money on a one-off build, but we can certainly get a better thermally efficient build. We're going to get good fabric, we're going to get low U values, and we're going to reduce our thermal bridging. Muck away. So there are builders out there having to deal with muck. It's very, very costly, and it's getting more costly as the years go on. There's one developer out there that bought 2 landfill sites to try and deal with muck away. So if we're pulling less muck out of the ground, we're going to save money. And if we're using underfloor heating, it's going to work more efficiently with an insulated foundation system. We're not going to have as much heat loss because we're going to deal with our thermal bridging at the perimeter, and we're going to utilize our thermal mass. And with an insulated foundation system, our U value we're typically seeing is 0.1. So we're blitzing any requirements of the building regulations. Part L states if we're underfloor heating, we need to get to a 0.15. By using this system, you're going to get to around 0.1. So we achieved the agreement cert for our foundation system last year. This was 2.5 years of hard work, but it was well worth it because we are Ireland's only NSAI agreement certified foundation system. As part of that, obviously we have our NSAI cert. And again, depending on where you are in the process of building and designing, we've all the documentation and the services to back up and provide the technical support for that. So if you're an engineer, we have a structural design guide taking 3 examples how to design the system. If you are an installer or looking to use the system, we have an installation guide. We have an online training platform for that as well. If you are a designer, we have typical details with thermal modeling for that as well. So there's a lot of background information. So how does the system work? So we're taking a concrete floor slab and we're wrapping it in insulation. So we've a full wrap of insulation, a thermal envelope under the ground floor, and we return it up at the perimeter. And whatever the wall construction is, in this case, we're showing a block cavity wall, we line it up with whatever the insulation is in the wall. So we're getting this full thermal envelope and then continuing the insulation through the wall structure and into the roof. So very, very effective in reducing our thermal bridging. At the perimeter, what we do is we take our concrete floor slab, which is normally around 150 mil, and we thicken it. We thicken it to take the structural loads from the walls above it. So the inside leaf of the cavity wall here has the load on it. This is the one with the wall, the roof and the floor loads coming through it. And we're using a denser EPS. So this EPS 300 is very dense material underneath this thickening to take the loadings. On the outer leaf, we have a separate ring beam formed within the EPS. So that acts as a permanent formwork as well to take the outer leaf. So at all times, the whole idea is wrapping that ground floor. No thermal bridges. If this was a traditional strip, we'd have a strip here. We'd have walls coming up. We'd be trying to detail it, put in little bits of perimeter insulation here. Where we have the internal load-bearing walls, heavily loaded walls, or if we're looking at bigger developments, party walls. Again, if we were looking at strips, we'd have a separate strip. We'd have walls coming up here. And again, we're trying to detail around that to cut down our thermal bridge. With an insulated foundation system, there's no break in the insulation. Again, if we have a load of a wall here, we thicken the slab slightly and we use a denser insulation. So we have 300 millimeters of insulation in the main part of the floor, and then we use our denser insulation where we need to take the loads. So essentially, as I mentioned, we use the concrete slab to work for us and thicken it where we need to take the structure above it. It's used for ground floor construction and it's an engineered system. So it's only designed to suit the site that it's going to go on and the wall structure and the loads that's going to go on top of it. We use 2 types of EPS, normally EPS 300, where we need to take the structural loadings, and the EPS 100 in the main part of the floor. And obviously we have a small bit of concrete and steel reinforcement in that as well. So the idea is we use this EPS to take the loading. So this, we can see this in an L or an F shape at the perimeter, where depending on the wall structure. So this is this kind of F shape here that you can see here. That's the EPS 300. We can easily accommodate any of the different types of structures. So whether it be a timber frame, solid wall with EWI, external insulation, cavity wall construction, ICF or insulated concrete formwork, SIPS panels and steel frames. There's a lot of flexibility with the system that it can work with all the different types of construction. So some typical details again, just to show you how it works with the different types of construction. So this is a block cavity wall, and we've already seen this one here. So we've our inner leaf and our outer leaf. The outer leaf sits on the ring beam made by the EPS. So this is, I've outlined it in red here. So this is this F-shaped profile. The inner leaf sits on the thickened part of the concrete slab. Again, we have our dense material under it, but at all times, there's a full wrap of that ground floor. And as you see, the insulation comes up into the cavity and lines up with whatever the insulation is in the cavity there. Similar I suppose, approach is a timber frame with a masonry outer leaf. So we have our timber frame sitting here. We have this F-shaped profile again. So again, we have the wrap around the concrete slab, high amount of insulation under the floor. If we're looking at the solid wall construction with EWI, or we're looking at something maybe like an ICF construction, we have what we would call this L profile at the perimeter. So you can see it's a simpler detail to achieve. But again, it's the same idea. We're trying to wrap the ground floor slab and line it up with whatever the insulation is going to be of the wall structure. So with that full thermal envelope all the way around the building. Again, trying to make life easy for us. Get the fabric right. Get your heating systems working efficiently, and you're going to save yourself a lot of hassle. So we looked at some thermal bridging, some energy efficiencies of a typical build. As I mentioned, if you're using underfloor heating, this would go straight into the concrete slab of the foundation system. And because we have so much insulation below, because we have the perimeter detailing done very, very well, so we're not having a thermal bridge, the underfloor heating systems themselves will work very, very efficiently. Interesting to note. So as I mentioned, we have a lot of thermal modeling done, and this is very effective work if you look at the deep software and getting into your BER calculations. So if you model a typical building, which we did, it was a semi-detached property that we were supplying a foundation system to, and we got the thermal modeling done. So the FRSI, which is the temperature difference inside to outside, was 0.93. So that has to be above 0.75 for compliance with building regulations. We worked out our thermal transmittance, so the junction at the wall and the floor, which is a psi value. We've worked that out. But the interesting thing is when you come to the Y values. The Y value is when you look at every single thermal bridge, every junction in the building, and you get an overall thermal bridging value, which is a Y value. If you use the ACD, so the standard details that are in the industry, you can only use a standard psi value. You can only use standard values to go with those details. If you model the junctions, if you do what we've done here, you can use all the figures that go along with those. So when we did that, the Y value came in at 0.037. Now you compare that to the Y value if you use the standard details is 0.08. So there's a huge difference, which means that when you do that, you get your fabric right. You need to lean less onto the other parts of the build. So you might need as much on the solar and the PV and that kind of stuff in the build. So not only can you possibly save money with something like a foundation system, but you can possibly save money further up the build also. So a couple of case studies and some real life facts and figures, just to give people some understanding of how the system works from the foundation system. So this was a one-off house, obviously, built in Ballymore Eustace in County Kildare. The contractor and the architect had never used the foundation system before. The client was very interested in using the foundation system, and they decided when they developed the design with the architect, they wanted to go for a certified passive house. The contractor had never used a foundation system before this, but since then, him or his crew, they don't want to use traditional builds. They don't want anything to do with strip foundations anymore. They achieved some really, really impressive U values and performance factors with the build in this case. So when they used an insulated foundation system, they got a U value of 0.09 in the floor. Their building regulations required 0.15 because they were using underfloor heating. They used a 250 mil of an EPS board on the walls, external insulation, and they got a U value of 0.12. So some very, very low U values there, well below the building regulations. Now, we would say to people typically, maybe with a one-off house, it might work out around cost neutral, so possibly around the same price as a traditional build, but you're going to get a lower U value. You're going to solve some of the thermal bridging issues as well. But as can be seen from the costings that the contractor provided us with, you can actually save some money on a foundation by using an insulated foundation system. So you can see 36,000 against 32,000 roughly. So a nice difference there of 4,700. Big saving is on the screed. So we're not using an additional screed. We're using the thermal mass within the insulated foundation system to act as a heat store for us. Looking at, I suppose, the bigger scale. So this was a couple of years back. It was Ireland's biggest certified passive house development in City West, County Dublin. Durkin Residential, they were building a third phase of a residential development. Phases 1 and 2 were standard builds, good energy rated houses. But for phase 3, they decided they wanted to go back to the drawing board and do things slightly differently. So they used an insulated foundation system and they used external wall insulation. And again, by using the foundation system, they blitzed any of the requirements of the building regulations. So they achieved a U value of 0.1 on the floor by using the foundation system. They got a nice low U value on the wall of 0.16. Between the roof and the windows, again some impressive figures there. So the big thing, and there's a lot of pressure, and again, coming through like that thing I showed at the start with the poor individual with their head in their hands worrying about everything. People are saying that with the change to Part L, it has an implication on the bills that, oh my God, it's going to cost us more to build. But if you look at the fabric and getting things right from that point of view, look at your underfloor heating systems, get a good performing system that's going to work well with something like an insulated foundation system. There's not necessarily a cost implication, because these guys were able to sell a fully certified passive house in phase 3 at the exact same cost as the houses in phase 1 and 2. So they showed that if you look at things a little bit differently, maybe work efficiently, select the right fabric, the right systems, that you don't necessarily have a cost implication to reach the values that we need to go to. Some of the comments from site were just simple things like the site was cleaner, there was less muck, because we're dealing with strip foundations. We're putting down a stone base to build a foundation system on. So this is a picture from the site itself. So you see this L-shaped profile, and this is a mitered corner. So what we would do is we'd supply all this material cut exactly to the size of the house. We would give them an installation drawing. It's color coded. It has numbers on it. It's very, very simple for installation. You just follow the numbers. You put corner 3, corner 4 together. Piece 1 goes here. There's no cutting of that outside perimeter material on site. Reduce skilled labor. So if you're using a block layer, the block layer doesn't come in until your ground floor is in. If you're using a block wall, less concrete and blocks, less embodied carbon, less material, less impact on the environment. And they felt that their QS role was easier and definitely a quicker build time for them. Here's an example of some costings against strip foundations, raft foundations, and an insulated foundation system. So if we compare an insulated foundation system to a raft, there's easier detailing from the steel point of view. We're building on a level platform. So the steel requirement is not as high with an insulated foundation system. So looking at a pair of semi-detached houses, there's a nice saving insulated foundation to strip, and definitely more so over the raft foundation. In fact, there was one customer last year who used our foundation system on a development 30 odd houses, and they were suggesting actually their cost savings were more. Okay, I have a couple of more slides, and then Liam will be taking over. So just one thing to be aware of are EPDs, environmental product declarations. So we were the first board manufacturer in the country to get this, and this essentially states your environmental impact of your product from raw material through production to the time it arrives on site. So if you're using performance software like LEED or BREEAM, when you're using a product that has an EPD, it means you get your energy ratings a lot easier. And I suppose just some of the background work that we can help you with. If you have anything, and I'll pop up my email now in a second again, we can help with U-value calculations. As I mentioned, compliance with the regs. We've CE mark and NSCI certs, DLPs, a lot of construction details. If you use BIM, Revit, we have NZEB compliance details on our site you can download. Retrofit, if you're looking at retrofit projects, we even have a department that just purely helps with grant funding and that kind of thing. So there's a lot of things that we do in the background to help you deliver your project. So when you look at something like the insulated foundation system, hopefully you can see that certainly you can save on our time and our labor. We can certainly build faster, and we can possibly save ourselves money. And when we're using something like an EPS, our environmental impact isn't as high. We have that EPD there. It is a recyclable material, and it will last the lifetime of the build. And that's me. That's a quick run through on floor and insulated foundation system. There's a lot more to it, obviously, but just an overview and a flavor for it. That's my email address there. Feel free to pop me any emails, no matter what it is. If it's not for me, I'll get it to the right person. And thank you very much. And Liam Jordan from Uni-Therm will be taking over now.
So hello everyone, thanks for joining our CPD today. Thanks Andrew for that, very informative on your insulated foundation system and your core floor. My name is Liam Jordan from Uni-Therm Heating Systems, and welcome to our online CPD on meeting Part L 2019 with KORE and Uni-Therm. There's my email there on the bottom, so you want to take note of that. Any queries you have, you can ping them on to me there later on, or any queries going forward, either. Like, I'm there for any technical questions you may have. Just the contents to run through these. So my side of things in this CPD. So I'll just go through Uni-Therm and who we are and what we do. Talk to you on technical guidance document Part L, Part F, and INZEB. Go through underfloor heating, low temperature heat pumps, the integration of these then with KORE's Insulated Foundation, and something on compliance and certification then to sign off, and finish it at that. So Uni-Therm. So Uni-Therm Heating Systems was established in 2004. We have offices nationwide, one in Galway, Dublin and Cork. We provide heating system solutions for residential and commercial projects of all scales throughout the country. All projects are led by a qualified engineer, and we stock a range of quality products from a broad range of manufacturers. So that's just our streamline there. It's a bit on design. As with new building regs, TGD Part L and Part F 2019, we can easily design compliant, efficient heating systems just off the house plans by using heat loss calcs and backstop U values. It's a retrofit job, then we will liaise with the BR assessor and organise a site visit. So all products are tested and certified for use in the Irish market, and all our systems are designed to ensure Part L compliance. This video is just running here just to show you, just while I'm going through this, to keep you occupied. So system design is complete with integration of mechanical and electrical components, and I go through some technical drawings there again. So we design underfloor heating and high efficiency RAD systems to meet the heat loss calculations and comply with building regs. So here are just some of the technical drawings then that we supply. So we say controls drawings there for, we'd say stats, motorized valves, underfloor heating, actuators. There's a second fix schematic. So we do first fix electrical, second fix electrical, mechanical schematics for every project individually. There's thermostat layouts for the electrician, manifold layouts, radiator layouts, steel or radiator, steel or aluminium, and then underfloor heating loop plans. So ground floor, first floor, second floor, whatever is required, and they come with heat loss calcs on them as well. So the HRV then, so that's a Frankische unit exploded, best practice duct layout, and then duct runs for a specific job. So that's just a quick run through over some of the technical drawings that we supply. So speaking of supply, so we have one engineer for each project, and then every engineer has a balance of customers, and this just gives customer satisfaction. So every customer, installer, engineer knows their in-house engineer. So they're dealing with the same person, they know what they want, and this kind of makes sure that orders get processed on time as well. As seen in the previous drawings, full system schematics, these get sent out with each delivery. And there's communication between the merchant, the installer, the builder, and the homeowner. So like the engineer, in-house engineer, keeps in contact with all his customers and lets everyone know how things are going. It kind of avoids any confusion as well with orders on site. So all orders are split into first and second fixes, and this avoids any complications. And there's next day delivery then to location of your choice, whether it be into your branch, Brooks, Chadwick's, whoever it may be, or on site. So on site delivery there, location of your choice. So a bit on support then, installer training. So we offer in-house and online installer training. We had Daikin training there last Thursday and Friday with Martin Evans from Daikin, and the weekend before as well. We installer training. So all models are up and running in the showrooms for training and troubleshooting purposes. The installer knows their in-house engineer as well, said there previously, and dealing with the same person every time. So along with the full system schematics, we also do and have setup videos for installers. We have these for each individual unit. Then there's also over the phone technical support and on-site support as well when needed. Then on commissioning then, so we have a pre-commissioning form. It's just filled out by the installer, and it just makes sure the work is carried out as per Uni-Therm schematics and Uni-Therm's design. As I said, we have technical support there as well, so if there's ever any issues on site or anything, we're only a phone call away, or we can out on site as well. So we supply all compliance documentation for all our projects, on-site commission of heating system, and we then produce the commission certifier. So the homeowners are present, we can run through optimal operation there as well. So when the service engineers run through optimal operation and best efficiency practice as well for the system installed. Now I'm just going to get into the good stuff. So that was just a small bit there on Uni-Therm. Now I'm going to talk to you about technical guidance document on the conservation of fuel and energy in dwellings, and that's TGD Part L. So this document implements Articles 7 and 9 of the EU Energy Performance of Building Directives in Ireland. So that's the EPBD. Quick overview of changes to TGD Part L 2019. So start at the start there, I suppose 2005 is we're taking it as a baseline. So in 2005, we've seen the introduction of the energy performance coefficient. There's a non-dimensional figure that expresses the energy efficiency of a building. And this is based on the energy consumed for heating, hot water, ventilation, lighting. I think it is also calculated for humidification and cooling as well, but we try and design buildings without these in Ireland, you know. So this is calculated in the deep software to comply and must not exceed the maximum permitted energy performance coefficient. And as you can see here, there's a trend in reduction in primary energy consumption year after year to meet our renewable energy targets. So the maximum permitted energy performance coefficient is down from 0.6 to 0.3, and the maximum permitted carbon performance coefficient is down 0.69 to 0.35. We also seen the introduction of the renewable energy ratio of 20%. This is ISO 52000. So that's 20% of the total energy consumed by the building has to be from renewable sources on site or nearby. Basically just a graph showing the same thing again, starting on a timeline scale. So 2005 is your baseline there once again. And that's what the red line shows. We've consistently lowered our threshold in primary energy consumption. So time after time in order to meet our renewable energy targets, so our European renewable energy targets. So we're a bit away from that yet. And I think by 2030 there, we're trying to get carbon neutral. A small bit away from that yet. Bit on TGD Part F, so technical guidance document Part F on ventilation in dwellings. So natural ventilation is out the window due to the reduction in the air permeability backstop. This is brought down from 7 to 5 meters cubed per hour per meter squared. So this is making the new dwelling airtight basically. So ventilation is controlled mechanically instead now of conventional passive vents. Constant operation ensures removal of CO2 and volatile organic compounds for excellent indoor quality. So mechanical ventilation systems have to be designed, installed and commissioned by a competent designer and installer as per Part F 2019. And this obviously just came in there November 2020. So there we go, natural ventilation is acceptable anymore. And as I said, mechanical ventilation has to be designed, installed and commissioned by a competent designer and installer. So I suppose just a bit on mechanical ventilation then. So the types of mechanical ventilation here will include centralized extract ventilation. This is basically a constant extract from wet rooms. So your wet rooms are your kitchen, your utilities and your bathrooms. So just constant extract supplying then through trickle vents in windows or OPEs in the wall in your living areas. Demand controlled ventilation. So this extracts from your wet rooms when a humidity sensor is triggered. So there'll be a humidity sensor in your unit or in your ducts. And when this meets your relative humidity set point of usually around 60% RH, it just boosts the fans then to bring it down to ideal thermal comfort of 45 to 55 RH. Heat recovery ventilation then is probably the most popular one, especially for single-use homes. This extracts warm air from your wet rooms while heating the fresh air from outside to your supply room. So basically, I'll just actually talk to you a bit more about that in the next slide. So mechanical heat recovery ventilation. So reduces heat loss through ventilation. So with ventilation losses being the biggest contributor to fabric heat loss, by making our dwelling airtight and using heat recovery ventilation, we're significantly improving on energy performance. So the extract and supply ducts feed into a heat exchanger, and then without cross-contamination, they transfer heat from the warm air to the cold air. Usually the efficiency of this is between 85 and 90%. So if you had warm air at 22, for example, and your cold air outside at 5, the supply air to your living rooms and bedrooms will be about 17, 18 degrees, depending on your efficacy or your efficiency of your heat exchanger. So you've no compromise there on thermal comfort, as fresh air is preheated through the heat exchanger before entering the envelope. And our systems as well there, as I talked about, the humidity sensor and the DCV our heat recovery systems here in Uni-Therm, our Blauberg systems, use humidity sensors to boost the fans when this set point relative humidity level is reached. Small bit of NZEB here now, we'll just go through it so we'll all, I suppose, what is NZEB really? So Article 9 of EPPD, the European Performance of Building Directive, states that member states are to ensure that all buildings are nearly zero energy buildings by the 31st of 2020. So a nearly zero energy building, what's that? So it's basically a building that is a very high energy performance. So our building that uses nearly zero energy. So the nearly zero or low amount of energy required should be covered to a very significant extent by energy from renewable sources. This is including energy from renewable sources produced on site or nearby. So I suppose this is where heat pumps come into play, like your on-site renewable energy production. So heat pumps have become increasingly popular as their renewable source of energy. A low temperature air source heat pump ticks all the boxes. When it comes to compliance, ease of installation, consistency of energy production, they have a high COP, so that's coefficient of performance, low running costs, and they're easily maintained, easily serviced. Preventive maintenance is very easy once a year. So low temperature air to water heat pumps operate most efficiently at 30-35 degrees. And this is why we utilize underfloor heating anytime possible, because underfloor heating, we have a larger floor area and a smaller flow temperature. Going to talk to you about underfloor heating. Just don't know the level of people here now, so just going to give you a quick run through on underfloor heating. So here we have a few section drawings of underfloor heating in a photograph. So that's 150 mil centers there, ideally 75 mil screed with your 16 mil PEX pipe, and your generally 150 mil insulation onto your concrete slab. So underfloor heating is defined as that which warms the floor structure, including the floor surface, in order to heat the room or the space above. So here you can see a cutout of the standard underfloor heating system. Traditional methods, the floor insulation is bedded on top of your concrete slab, and then there's the vapor barrier placed on top of that. This is then pipe tracking is used, or rapid rail as we call it. That's clipped down, and that accommodates the array of pipes at 150 mil centers. Sand and cement screed is then poured on top to create a thermal mass. So usually your sand and cement screed there is 75 mil for ground floor. The Kim floor screed or the liquid screed is generally 60 mil. But like that, just for your thermal mass in your floor, 75 mil sand and cement is standard. So why underfloor heating? So I suppose, as the floor is your emitter, as I said there a while ago, instead of traditional systems emitters such as RADs, we now have a much larger area. So we can utilize a lower floor temperature. So the bigger the area, the less or the lower the floor temperature we require. So the lower the floor temperature, then the higher the efficiency of the heat pump and the lower the running costs. The thicker the screed for the underfloor, the more thermal mass it will have and the more radiation it will produce. So that's what we're getting to here now. So just something here from the underfloor heating design installation guide. So the method of heat transfer from the heated floor surface is circa 55% by radiation, plus 45% by convection, plus or minus 5%, depending on the surface to air temperature differential. Because the majority of the heat is radiant, it creates occupancy thermal comfort at lower air temperatures than what would be expected from radiators, convectors, and warm air systems. So we're basically just saying, because it's from your standard 75 mil, that's based on standard 75 mil standard cement screed, majority of your heat is coming by radiation, and this gives you more thermal comfort. So if we increase the thermal mass, we're increasing the amount of radiation and therefore increasing the thermal comfort, and we'll get away with lower temperatures. So bit on low temperature heat pumps here, LG, Daikin, Hitachi, all our heat pumps in the Uni-Therm here, basically they're all R32 refrigerant. So we're going to talk to you a bit now on the LG Therma V R32 monoblock. It's the world's first R32 monoblock. The R32 refrigerant, you hear me talking about that a lot, or you hear it a lot now. I suppose it's sort of saying it's the 5th generation refrigerant, or what is R32? So R32 is replacing R410A. R410A is probably in every fridge or heat pump now at the moment, but it's been phased out by 2025 due to its high global warming potential. So I think the global warming potential for R14A is 2088. So obviously the higher the global warming potential, the worse it is for the planet. So the R32 is 675. So it's less than a third, or more than 2/3 less damaging to the globe compared to R410A. So the ideal solution for both new builds and also retrofit projects due to its wide operation range. So you have a wide operation range there of 25 to 65 degrees without the use of a backup heater. So like that's fairly unheard of there, is heating to 65 degrees without the use of a backup heater. Usually you're heating to 50 without a backup heater, and then the backup heater is probably getting you up to 60 then to do disinfection once a week or once every 2 weeks. So for NZ buildings there, where our weather com flow is typically between 32 to 38 degrees. That's based on a 75 mil screed. So as I said there, running at lower temperatures gives minimal input with higher COP values. So how are we getting up to that 65 degrees? Well, there's a new type scroll compressor in this LG Therma V, and it varies running frequency with precise control. And the lower the flow temperature required, the lower the frequency and the lower the bills. So still though, how do we get that enthalpy to get us up to this 65 degrees, whereas an normal split heat pump will only get us up to 52, 53, maybe 55. So this is a flash gas injection. So our wet vapor injection is also called. So you're compressing at low temperature, low pressure, and you get up to your certain stage when you're reaching max compression, high temperature, high pressure, and then it gives it, what it does is it gives it a wet vapor injection, which cools the compressor and allows it to compress even further, creating even increasing the enthalpy dramatically on the thermodynamic cycle. So this is what gets you that extra, basically nearly 10 degrees or more from the thermodynamic cycle. Just going to have a quick look here at the capacity tables for what is it, a 7 kilowatt LG Therma V monoblock. So we'll just highlight the, I suppose, the test standard there. EN 14825, air at 7, water 35. So that's what all our heat pumps are tested at here. So as we can see there, we have 100% performance down to -7. So -7, you're 7 kilowatts, the COP at 2.96, all the way up obviously from 35 degrees down to -7. And this total capacity 7 without a backup heater is 7 kilowatts even down to 60 degrees leaving water temperature. So great for retrofits, great for any application with the wide operation range. But we'll just have another look here at our, so what I'm looking at here now is running at even lower temperatures. So if we increase the thermal mass, we can get away with even lower flow temperatures, lower leaving water temperatures. So we'd say design conditions here in Uni-Therm, you're designing at -3. So basically worst case scenario, on average, the weather in Ireland is generally 10 degrees on average. That's what they say. The weather in Ireland is 10 degrees on average. So at a 10-degree average weather, it's 7 kilowatts, you're getting a COP of 5.14. So for every 1 unit of electricity you put in, you're getting 5.14 out. Now we take a worst case scenario, we'd say even down to -7 there at 1 in every 20 years winter. You're still getting 3.15 units for every 1 unit of electricity. And on average design temperatures there, -2, 3.5. So on average there, you're still getting a COP of 4 all year round for your LG Therma V. And the 5, 7, 9, 12, they're all the same. They all have 100% performance. And this is again due to the wet vapor injection and your new scroll compressor. So there's a low degradation there of the coefficient of performance. Right, so integrating our underfloor heating system with our low temperature heat pumps and KORE's Insulated Foundation. So as I said there, complete peace of mind in those cold winter days with the LG Therma V, as you're guaranteed 100% performance down to -7. With KORE's Insulated Foundation System, exterior wall to floor thermal bridging is eliminated. And this gives your underfloor heating great relief at external walls and takes pressure off the system in those colder north-facing rooms. So with floors and external walls being big contributors to heat loss, we've considerably lower heat load to consider, which lowers the required heating capacity and basically brings down the capital cost and running costs. So lower heat load, lower heat bills, lower bills. So just, I suppose, the floor build up here for KORE's insulated concrete foundation. But I suppose we start with where our earth there, so our compacted gravel on our site. Then we go with 150 mil KORE ETS installation. So that's 150 mil on average, as Andrew talked about there recently. It goes from 100 to 300, but 150 on average. Then you have your vapor barrier required, rapid rail pipe tracking, so pipe tracking, 45 mil clips, so clip the tracking into the insulation, 16 mil PEX PEX underfloor heating pipe, so it's PEX with an aluminium oxygen barrier and PEX again the outside, so 16 mil pipe, and then 150 mil reinforced concrete. So this is basically our thermal mass that we're talking about. So instead of going concrete insulation screed, we're going just insulation concrete slab, aka our thermal mass and screed. So with twice the thermal mass here, we're looking at getting out twice the radiation. So as mentioned previously, for a 75 mil screed, the method of heat transfer from the heated floor is about 55% radiation and 45% convection. But with 150 mil slab and 775, we've doubled the thermal mass in the floor. So we've significantly increased the longevity of radiation from the floor. And because the majority of the heat is now predominantly radiant, it creates occupancy thermal comfort at even lower air temperatures. So that's a big thing with radiant heating there. You don't need to have it up your 21, 22 degrees to get that thermal comfort. Like, you know, you can, even at 18, 19 degrees, the more radiant the heat is, the more you feel it on your body. So now we can utilize the thermal mass to run our heat pump with a low temperature weather compensation curve. So we can charge the floor so it can radiate throughout the day. We can get a steady state temperature. So optimum performance can be gotten from the machine by charging the whole slab with a low flow temperatures of 26 to 32 degrees. So basically leaving your system open, letting it run when it wants. So by running an inverter driven compressor, sorry, I'll just go through that there just to see. By running an inverter driven compressor in the heat pump continuously, the load is always very small and the LG ThermoV doesn't have much work to do. So if it's just tipping away the whole time, keeping your leaving water temperature at 26, 28 degrees, we'll say, for an outdoor ambient temperature of 10 degrees, like today in the west of Ireland here, it's probably about 10, 11 degrees. So I don't know what it is over in the east there. It could be up at 16 degrees, but at 16 degrees there, we'd be looking at even lower flow temperature of probably 27 degrees or 26. And that's still heating enough heat to heat the thermal mass and radiate off it. So that'll be left running continuously. The load isn't great when you leave it running at your leaving water temperature like that and your low temperature weather compensation curve. So you could just be with one of the lads here in the office actually has a trial and tribulation with his Hykumo Pro, and he's just testing it out and he has all the data there, and it shows, you know, if you're running it for all your stats open, it's kind of like it's coming on and off and on and off, but there is a way of doing it. So you can just basically let your flow temperature run and you're just getting to the set point thermostat. So there's a bit more with commissioning for this, but once you get it right, you're nearly half in your bills. So there we go, something about low running costs. So bit on compliance and certification. So that's generally the design idea there. All of our products are CE marked, so they're tested to current EN standards, and we liaise with the BR assessor for the homeowner and supply them with the Deep 4.2 inputs and the eco design data, designer installer sign-off forms, whatever technical spec they need, technical fiche. We also supply ancillary certs for design and completion with inspection certs on request. And we're members of the Heat Pump Association, so we work in conjunction with SAI on compliance. Designer installer sign-off form. So basically just signing off each project. So it states the type of heat pump installed and the project, verifies running parameters. Designer installer sign-off is needed by the BR assessors, as these parameters are entered into Deep 4.2 to quantify the heating and hot water performance. So this is just a basic example of it there for your LG ThermoV 7 kilowatt. Then we have a heat and design tab. It's completed for the BR assessor along with the SR50 heat calculation. So as you can see here, we have RADs present. So when there's RADs present, we do a full SR50 heat loss calculations for the BR assessor and the engineer involved. It gives the total heat loss for the building. So the total heat output of emitters installed and the design heat loss indicator. So you can see in that building there was down at what 1.49 is the HLI for a 253 square meter building. So a bit on compliance. So this is our deep 4.2 input. So if we all know deep 4.2 or the BR assessors do, there isn't as many views there was before. So we engage with the BR assessors. When we had deep 3.2, we used to fill out all the XMLs here in house in Uni-Therm, but now you can't share access. So we just do screenshots of sheets there for each individual heat pump and each individual design, and we send that on to the BR assessor, and then we liaise with them, and they can give us a call and we'll go through everything with them. So we have the inputs into deep 4.2 are taken from the design installer sign-off form, from heating supplier, and eco design data from the manufacturer. So yeah, so again, there's heat pump test data for generally a low and a high test condition, 35 and 40, 55. So these are tested in factory for test standard EN 14825, which is our heating test standard. So that's just something on that. So again, our same again for our water heating test standard. So 16147, and this is provides hot water efficiency, declared load profile, and standard standby heat loss for deep 4.2. So there we go again, hot water traps, so distribution losses, storage losses declared as part of standard EN 16147. There, once again, design flow temperature, daily operating hours, backup space. So this is all taken from designer and installer sign off. I just run through it quickly. That's from our manufacturer then. So that's our eco design, our technical feat. So there are your figures. So they're backup figures as well. So we'll tell you what to input, show them what to input, and then give the backup figures so they can double check everything is 100%. Same as 16147. And then we just a bit on ancillary starts. So we design and inspection and completion. These are all available on request. And I suppose last but not least here, I have just basically on commission. So on our commission starts issued from the manufacturer with serial numbers of units installed, the type of system, the control on the system, commission checklist. So our service engineers on site have to go through a series of checks, and this is signed off and commissioned. If there is anything out of the ordinary, they'll note this, and we might have to call out for another site visit again, or else maybe photographic evidence might do. So from the date of commission, the extended 5-year warranty is in place, and should any issues should arise, you contact Uni-Therm service department and it will be dealt with promptly and immediately. So thanks for your time, everyone. That's myself, and I gave you my email there a while ago. It's liam@unithermhs.ie. If you have any queries, just pass this over now again.
Thank you, Liam. And if anyone has any questions, we have a Q&A box just on the bottom there, if you'd like to pop your questions in, and we'll get the guys to answer them. So first off, for yourself, Andrew, our first question is there a load or height restriction with the insulated foundation system?
Thanks, Lisa. So just on that, if we're looking at something like a heavy construction, masonry, cavity wall construction with maybe precast floors, that kind of thing, you would be looking at maybe 2.5 stories as the limit onto an insulated foundation system based on our current design information. If you're looking at a lighter, I suppose, timber frame, steel frame, 3 stories shouldn't be an issue. Actually looking at one timber frame 4-story development for an architect at the moment as well. When you get into, I suppose, the timber frame stuff, it's the block work that's sitting on the external leaf, again, can be a bit of an issue. But kind of 2.5 stories for block, 3 stories for timber frame and steel frame are kind of the guidelines.
Thanks, Andrew. And just another one came in there for foundation from Dennis. What type of ground conditions would suit the foundation system?
Luckily, it works very well with most conditions. Even poor soils, the foundation system can work very well and in fact can solve maybe some issues. So under the foundation system, there's a buildup of compacted stone. There's a T2, about 200 mil, and then there's a T3 stone at the top of that, a blinding layer of 30 to 50 mils. There was one site we did in North County Dublin. There was 2 houses. They were 20 feet from the beach, basically out in Rush. And one of the sites they were looking at piling it, by building up a heavier stone build up underneath the foundation system, they actually got away from needing the piling in that scenario. So once you have a compressive strength in the soil of somewhere of around 100 kPa, 100 kilonewtons per square meter, that's kind of the minimum for a standard foundation system. As I said, we can look at different scenarios for it, but obviously if you've more bearing capacity in the soil, that works equally as well.
Thanks, Andrew. Liam, just a question for you here from Patrick regarding underfloor heating in pantry and plant rooms. Should this be avoided? Is there any implications for thermal bridging due to areas without underfloor heating?
Right. So hi, Patrick. So I suppose obviously we'll avoid underfloor heating in pantries for the sake of food, and we'll say food going off and heating the food and whatever else. So if you don't have underfloor heating in your plant room or your pantry, well, then obviously your heat is going to go from warm to cold. So whatever about thermal bridging through your internal blocks, we don't find as much of an issue. Obviously, it's different if it's actually escaping the thermal envelope. So which I should definitely avoid it in the pantry, and that's just to do with, as I said, food types and that side of things, and keeping your pantry cool. And as for the plant room, there's generally not any need because you have latent heat off the plant itself. So we design our systems with basically no underfloor heating in the pantry or the plant room, or even under, for that matter, when it comes down to the design of it, under kitchen presses and this side of things. So there's no need for it there. And obviously it eliminates the danger of someone piercing a pipe when they're putting in kitchen units or stuff like that. If lads have gone off there and ran their own heating, not looked at drawings, ran their own pipe work, done their own loops, they didn't have an idea where the kitchen was going. So we will liaise with the homeowner, the installer, the builder if needs be on a we'd say if it's a contractor build, and we'll just make sure that we know where the kitchen's going, we know where everything's going, so that we're not going to run into any issues there with bursting pipes in the floor. So that's something we would take care of.
Thanks, Liam. And just a question from Mark about the slides from today. Mark, this is recorded, so will be available on our YouTube channel later on. Another one for you, Liam. What is the lifespan for the heat pump? Does it need to be changed after 10, 12 years?
So generally, no. Good system design is everything when it comes to a heat pump. Like a compressor is just the same as you have in your fridge. It's the amount of on-off cycles you have. Now, by designing it so, like at Uni-Therm here, we designed the system so it can run for 24 hours, so it can come on and off when it wants. There's overview field settings in the different heat pumps that we change on commissioning, so that we have minimum on times, minimum off times, and this reduces the amount of on-off start. So we'd say it'll basically run longer, run for longer periods of time and have less on-off start. So we have units since Uni-Therm opened in 2004 out in the Ireland Islands, out around Galway, around Dublin, and they're there since 2004 and they're tipping away. Preventive maintenance is a big thing, and that's why we have our own service department, is just to look after what we have supplied. And you know, so like that, we have them in 16, 17, 18 years, like, and there's no issue with them. Preventive maintenance once a year, maybe every 2 years after the first couple of years, but every year preferably. Like, you know, it's a mechanical machine, like your car there. Would you go without servicing it after a while? Preventive maintenance, if you just drive it into the ground and don't do anything with it, it's not going to last you that long. But obviously, if you can do a bit of maintenance every year, she'll last a bit longer. So yeah, that's it.
Thanks, Liam. One for you, Andrew. How is the insulated foundation system coping with settlement in contrast to traditional strip?
I suppose the foundation system is actually more robust from its design point of view. For strip foundations, we generally go off tables. So 3 times the width of the wall equals our strip, and we're using that design information for every single site. So there's little or no structural design going into a traditional foundation. When you look at an insulated foundation, it's only designed by a structural engineer based on the site information, and as I mentioned, based on the loadings that are going on top of it. So these foundation systems have been used in Scandinavian countries for 30 to 40 years, and they have less issue with a designed engineered foundation over traditional. We have a known capacity of the EPS material that goes into it. We have a known capacity of the steel and the concrete, and we have a known capacity of the compacted stone. So there are less issues with an engineered system like this.
Thanks, Andrew. Liam, for a house with 100 mil cavity insulation and 2 inches on internal walls, no underfloor, aluminium rads up and downstairs, is it worth installing a heat pump, or should they revert to steel rads? That's a question from Eva.
Hi, Eva. Yeah, so I'd imagine there you're probably looking at a retrofit if you only have a 100 mil cavity, or do you mean a 150 mil cavity with 100 mil insulation? Either way, and then you have 2 inches on the internal wall. So, yeah, so heat pump will work with aluminium or steel rads. It just obviously the rads have to be sized on basically on your heat output. So, what's your duty? What's going into it? What flow temperature you're putting into the rads? So, at Uni-Therm here, we will design all our rads, whether it be steel or aluminium. Your aluminium is a higher thermal conductivity, so you can get away with smaller aluminium rads than you would with steel rads. Steel rads probably will be about nearly 3/4 of the size bigger, so 1.75 times the size of an aluminium rad with the same output. So you can, like when you say is it worth installing a heat pump, or should you revert to steel rads? Of course it's worth installing a heat pump. Like you're lowering your carbon footprint. You don't have any more oil, you don't have any more turf, whatever it is, you don't have any more dirt. So it's a matter of, it's efficient, it's more cost effective, and obviously the fabric of the building does make a difference. Like, so you seem to have enough there, 100 mil cavity insulation and 2 inches on the wall, so that's more than enough. And if aluminium rads ideally, but like that, steel rads will work if you have the wall space for the bigger steel rads.
Thanks, Liam. One final one now for you, Andrew. By building up an extra stone, won't that make it more expensive? What depth of dig for extra stone build-up would make it less cost effective than a traditional strip or raft foundation?
Okay, just to reinforce Liam's one before I answer that one, I put in a heat pump into my house with standard steel rads. Went from oil and works very well. Definitely saves money. It's a lot easier of a system. And now for this question. So I suppose it's the same type of prep that you're going to use. So if you're looking at a strip foundation and you're bringing up your rising walls, you're going to have an element of fill under, whether it be a concrete subfloor or under the insulation. So you're going to have maybe 150 to 200 mil of stone there. Anyway, it's exact same under the foundation system. So there's no additional cost. You're saving on that strip foundation, the concrete and the blockwork and the labor that's going into that. So there's no additional cost for the stone prep that's in the foundation system. Equally, if you're putting more stone into a site, say you were doing a sloped site and you had a larger amount of fill at one end compared to the other end of a site, it'd be the same with a strip foundation possibly. And again, it works out the same with the foundation system. So there's no extra additional cost typically with any stone build-up. That example that I mentioned earlier where they had 400 mil, so that was against piling a site. So you can imagine the cost that they would have spent on piling, and all they had was 200 mil of extra stone. They were saving a fortune. So there's no additional cost around the stone prep for a foundation system.
Thanks, Andrew. And just one more for you from Damien. Do you need to carry out a ground investigation or get the bearing capacity of the soil for the insulated foundation system?
Yeah, so that comes back to the engineer on site, whoever the structural engineers. Obviously, they need to do their due diligence to establish what they know to be the makeup of the soil. If it was a particularly, I suppose, poor site, or it was a large site, when you're looking at maybe into the bigger developments as well, they might have to do plate compaction tests along with the geotechnical studies, because if a site is so big, you might have a house being built over in one corner, the ground is one type of soil, and over in the far corner it may be completely different. So it's down to the due diligence of the structural engineer. We've had foundation systems go on to change of use sites where they've actually been putting in some housing into previous industrial sites where they're removing tanks and building up stone. And once they have the stone, they do their plate compaction test to get a known bearing capacity on the stone. So, I mean, engineers that they would be looking at ground investigations and site investigations regularly anyway. So it shouldn't be anything out of the ordinary for them.
Great, thanks, Andrew. And just to let everybody know, this session is recorded and will be available on KORE Insulation's YouTube channel later on today. And if you have any questions for Andrew, his email is andrewbutler@koresystem.com, and you can catch Liam from Unitherm at liam@unithermhs.ie. Thank you for joining us today. And again, if you have any questions and if you would like a CPD cert of attendance, you can email us marketing@koresystem.com. Thank you and have a great day.
Cheers, everybody. Thanks for coming.
Thank you.